So look over. So today we'll start with our Leibniz theorem, successive differentiation. Successive differentiation means when you do more than 2 times derivatives, one after another, then we'll do the successive derivatives. Clear? So where we'll apply why we need a Leibniz theorem, that is first very important. And first of all, today we'll prove only what? Proof of the Leibniz theorem. So what is the Leibniz theorem and the proof of that theorem as well. Okay. So that the pre-knowledge that you must require to proving the here Leibniz theorem is that the principle of mathematical induction, because in higher classes maximum proving part will do with the help of the principle of mathematical induction. This is called a first principle of induction. Remember that we have a two principle of mathematical induction. Clear? So this is your actually first principle of mathematical induction. This is called a first principle. So in this method, so will this method is useful for proving many many proving part that is for your natural number. Clear? That is for natural number. Clear? So how will prove? What is the step one? First, whatever if you want to prove, for example, if you know this 1 plus 2 plus 3 dot 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 n is 1, n plus 1 by 2, this type of relation also can be proved what with the help of the induction. Clear? So first of all, whatever be the proving part is here, you have to assume this as a statement. So this is the first cases. So let's suppose you want to prove this one. So Pn be the statement, you have to write down this. So this is the first cases. That means there should be a statement. Clear? So that means if Pn is a given statement and n is a what? Natural number. Remember that this is for the natural number. First step one in the principle of induction is that you have to verify that it is true for what? N equals to 1. N equals to 1. For example, how to prove n equals to 1? For example, here. So this is your LHS part, remember that, and this equals to right hand side part is a RHS part. Clear? So look over. If you put n equals to 1 means what does it imply? If it is n equals to n, then it ends at what? You are writing the natural number, adding the natural number till n. If you write p5, that means it implies that you are writing a natural number till 5. Till 5. But you have to prove for what? You have to verify for n equals to 1. So if I put n equals to 1 here, so you just have to add one natural number only. Am I clear? You just have to add one natural. So one natural number is 1. Yes or no? So one natural number is 1. This is the LHS part. So in RHS, when you put n is equals to 1, you are putting n equals to 1. Remember that. In LHS, you are getting 1. In RHS, if you put n equals to 1 plus 1 by 2, so you will see 2 and 1 plus 2 is also 1 plus 1 is also 2. So you are getting LHS equals to RHS. That means the theorem is proved for n equals to 1. This is the first step. Clear? This is done. So first you have to verify whether the statement is true for n equals to 1 or not. This is the first principle of induction. The second is that you have to assume that the Pn is what? Pn is true for what? N is equals to m, say some natural number. You are just assuming that it is true. If it is true for n is equals to m, so can we say that Pm is the 1 plus 2? That means you are adding natural number up to where? M. So you can write this as a m plus 1 by 2. Am I clear this one? Clear? So now last step and a very important step is that you have to prove the step 3, that you have to prove that it is true for n equals to m plus 1. Now, till now if you notice here, this is the assumption part. So I am writing both LHS and the RHS. But now you have to prove what? You have to prove the Pn is true for n equals to m plus 1. That means you have to prove, you have to put n LHS m plus 1, then it should end at what? M plus 1. Then RHS answer should be what? Here should be m plus 1, here should be m plus 1 by 2. You have to prove that one. Clear? So that means if Pm plus 1 is there, now we have to prove what? You have to write down. Okay, now we have to prove for Pn. We'll do in the main theorem. Clear? So Pm plus 1, look over it. So then it is what? 1 plus 2 plus 3 plus 4 plus dot 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 m plus 1. Any doubt up here? Clear? So now can we say that just before that, what is the values? Because it is just m only. Yes or no? So it is m, and then here m plus 1. Am I clear up to here? Because 4 in back value it is 3, then m plus 1 is just back one value is m. So as you have already assumed this is true for m plus 1, so can we write in place of this m plus 1? Because remember that in induction whatever you have assumed you have always apply over here. Any doubt up here? Clear? So what is common? M plus 1 is common. So when I simplify it, m plus 1, So you are getting m by 2 plus 1. Yes or no? Because when you common this one, you are getting m by 2 plus 1. So when you take the LCM, you are getting m plus 1 and then m plus 2 by 2. Isn't it? This can be written as a what? M plus 1 and then m plus 1 by 2. Any doubt? So that means you see that whenever it is n, it is n plus 1, and whenever it is m plus 1, it is m plus 1 and m plus 1 plus 2 1, because 2 can be written as this. That means we have proof it is true for n is equals to m plus 1. So by principle of mathematical induction, then it say that it is true for all values. So this is very important to prove maximum theory in the higher classes, that the principle of using the principle of, clear. So this concept that you need in proving the Leibniz theorem, first concept. Any doubt up here? Clear. So this is the concept. That means you have to know how to prove any theorem using what? Principle of mathematical induction. Why I am explaining this? Because in class 11, this in CBSE in 2024, it is omitted from the syllabus. That is why this is from class 11 actually. Clear, but it is omitted from the CBSE syllabus. That's why first I am explaining this. So now listen carefully. So now the sum combination property that you must know here. Let NC0, that means NC0 or the NCN is what? 1. This you must know. Any doubt? Clear? For example, 5C0 if I write, that is 1. If I write 6C6, it is 1. That means if the this and this are same, it is 1, or if the this base part R is 0, then also it is 1. Whatever be the n values. Next is that NC1 is what? N. NC1 is n. That means example, if I write 6C1, you can write this as a 6. Clear? Or if you write suppose R plus 1, you can write this as a in play in terms of the combination, you can write this also. Both are same. From here to here, if you need these values in the number, you can write in this way. If you read this value in terms of the combination, then you have to write this. You can write this. Am I clear? Okay. Next, very important property, that the NCR is same as the NCR minus 1. For example, if I write 5C4, that is equivalent to 5C, 5 minus 4 is 1. Both values are equal. This is also very, very important properties. Any doubt? Clear? Both values are same. Clear? If you notice, we have applied this in many probability chapter as well. Clear? So look over, okay? So I hope you all know that the how to expand the combination. Suppose it is 5C2. So how we can write this as a 5 into, how many times we'll write? 2 times. 5 into 4, then 2 into 1. You know how to expand the combination. Any doubt? If this is basis 2, you have to write 5 decrease up to 2 times, then 2 into 1. Am I clear? But what is the uses of these values is that if you have suppose 52C49, then it is very difficult to subtract up to 52 49 times. So best approach, whenever the base is very big, just subtract this one. So you can convert this to 52C3 as well. This minus this. Now it is easy to solve. You just have to write down 3 times 52, then 51, then 50, then you have to write 3, 2, 1. Then simplify it, you'll get the answer. Am I clear? Any doubt? Next part. Next part is when this n is same in the addition, and R plus 1, this is same as the n plus 1 CR. I am giving you the example. For example, if you have us here 8C4 and here is also 8C, it is just one less. It is just one less. Any doubt? When you add this one, the power, here you have to add 1 and you have to write down bigger. So 8 plus 1 is 9. See, then write down the bigger. Which is bigger, 3 or 4? 4. This is also very useful in your theorem. Any doubt? That means this property I'll mostly use this property in Leibniz theorem as well. Any doubt up there? Okay, that means the pre-knowledge to prove the here Leibniz theorem is that one is we'll prove the theorem with the help of the mathematical notation, and we know that in Leibniz theorem we'll apply combination also. I'll explain what is Leibniz theorem first. So now after that you must know the product rule of the derivatives. We know that whenever we have a two function ddx of u into v is u dv by dx plus v du by dx, or it is written as in this way. 1 means suffix 1. So you can write u v1 plus vu1. Yes or no? You can write in this way also. Clear? You can write in this way also, or u1v plus v1u. It's same only. Product rule. Clear? So now look over. Now Leibniz theorem. Look over. Now why we need a Leibniz theorem is that in class 11 and 12, what you have done, uv product rule of 1. And we have done double order derivatives also. But what if they will ask you find dd7 of x cube cos 3x? Then it's very lengthy. You have to do 7 times. So that's the reason why we need what? Leibniz theorem. Clear? So that means in first order and second order derivatives we have applied in class 12. But if there is a product of the function, but we are finding up to nth derivatives more than 2, then it will help you, that Leibniz theorem will help you to what? Solve fastly. Clear? So now listen carefully. So that means here to finding the nth order derivatives. So this one. So Leibniz theorem of nth order derivative of the product of two functions. What is a statement? Because the question may comes in this way in your college, that state and prove Leibniz theorem. So you must remember the statement as well. Clear? So let u and v are the two function of x that is differentiable n times. Then nth derivatives is this one. So look over here. Nth derivatives is u v n. So I'm again writing this one. Okay. So u v n. That means you are differentiating this two product up to how many times? Nth times. So you just have to, it is similar like a binomial theorem. So un write down v plus write down now nc1. Now u power will decrease and v power will increase slowly. Okay. So u power will n minus 1, then b suffix is 1. Suffix means differentiating that times. Am I clear? So next is what? nc2 u power u suffix is n minus 2, then v2. So on it goes on. If I take a middle values, if ncr, then what will be the u derivatives part? N minus r, and it is vr. So similarly at last you will get u and vn. So this is the formula of Leibniz theorem, which I've already written over here. So I'm not writing this. Am I clear? So now how to prove? So look over. Can I rub this one or look over? Better. So look over. So first we'll start our writing from in this way. Okay. Suppose this is the insert part. First you have to write down a statement. So we prove this theorem by what? Mathematical induction. Any doubt? Clear? So in mathematical induction, what is the first step? You have to assume the given proving part as a statement. Clear? So can we write this Pn such that, so this is be the statement. So I am assuming this be the statement. This is the first, that whatever you want to prove, you have to assume that as a statement. Clear up to here? Clear? So now what is the first step? We have to prove this theorem for n is equals to 1. So look over it. Okay. Very easy to prove this one. So can we write in this way? Remember that the suffix cannot be negative, because suffix denotes what? Derivatives. How many times you are differentiating. If suffix is 1, it implies that you are differentiating 1 times. 2. So it is always with a natural number. Remember that. Am I clear? So look over now. So putting n is equals to 1. Listen carefully. Okay. N is equals to 1. So P1 in LHS. Okay. So write down LHS and R. So in LHS. So P1. So that is UV1. You know how to differentiate this? Yes or no? Clear? So PV is equals to UV1. So can we write U1, then V, then V1, then U? Can we write this? What is the product rule? Product rule say that you have to keep one as a constant term, you have to differentiate the other. So I'm keeping V as a constant term, U1B. Am I clear? It is same only. So this is the LHS part. Clear? So in RHS, isn't it RHS is same? In RHS, if we put n is equals to 1, you are getting same. If we put n equals to 1, so U1 V plus what? Here we'll write 1C1 U 1 minus 1 0, you don't have to write down, and then v1. Any doubt? So we will not proceed because we know that we cannot write 1 c2, yes or no, because n is always in combination, n is always greater than equals to what? 2. Clear? Greater than equals to 2. So you have to stop here only. So if you solve, what is 1 c1? It is 1 only. So you are getting u1 v plus uv1. Isn't it both are same? Check it. Both are same. So therefore I can write, therefore the Pn is what? Pn is true for n is equals to 1. Any doubt? This is the first step of the induction. Clear? So now, next. Any doubt up here? So look over. So what is the second step? Second step is, we have to assume this statement is true for n equals to mc. Clear? N equals to mc. So now, let us assume that Pn is true for n is equals to mc. So that is, if it is true for n equals to mc, so we can say that, dear, so Pm is uvm. So that is what? You just have to replace the n by m. That's it. Am I clear? So it is um v plus mc1 u m minus 1 v1 plus mc1 mc2. Okay, this is 2. This is nc2. Okay, this is just wait. Okay, I have to rectify this one. Some printing error. This is u. Clear? So this is nc2 u. Clear? This is nc2 u. nc2 un minus 2. So look over. So then mc1, then mc2 u what? U m minus 2 v. Now listen carefully. Okay? Plus. Clear? So dotted figure. Listen carefully. Dotted figure. So can we write in middle value? This is m c r u to the power of u suffix is m minus r and vr. Then at last is what? Um uvm. uvm. Any doubt up to here? This does the assumption. Clear? So now this assumption up to here is actually easy. You just have to put n equals to 1. You have to just assume that's interchange by n. Main part is arranging the last part. Clear? So here we will apply all properties. So now you have to write down. Now we have to prove Pn is true for n is equals to m plus 1. Now listen carefully. Okay. Now listen carefully. So look, if it is m plus 1, so isn't it, if it is m plus 1, dear, if it is what? M plus 1, this one. So it should be differentiated one more times, yes or no? It should be differentiated how many times? One more times. So what you need is that if it is m plus 1, dear, it should be replaced by m plus 1, it should be replaced by m plus 1, it should be replaced by m plus 1 minus 1, so on. Yes or no? Then it is proof. Clear? So now listen carefully. Okay. So differentiating with respect to x. This one. Differentiating with respect to x. Clear? Just wait. Okay. I need this part. final part. So look over. So that means if we differentiate this one, clear? So now I am differentiating this with respect to x. What will happen? Can we write in this way, dear? If I differentiate in this way one time, so it become UBM plus 1. Yes or no? Any doubt? M plus 1. Clear? Because when you differentiate U1, if you differentiate one more time, it become U2. So 1 plus 1. So here you have to apply which rule? Product rule. So very important. So look over. First I am differentiating this. It will give you UM plus 1. Then V as it is. Now UM as it is. So when I differentiate V, it become V1. Any doubt? Product rule. Assuming this, what is the product rule? Product rule say that you have to keep one as a constant term, another one differentiate, plus another, and so on. Am I clear? So when I differentiate this, you have to keep this as as it is, so m plus 1. Again, when I keep this as a constant term and this you differentiate, it become b1. Similarly, look over. Since we know very well mc1 is dear what constant term, yes or no? So when I differentiate this, it become what? Ym minus 1 plus 1 only, yes or no? Then it is v1 plus, keep this as it is. When I differentiate v1, it become b2. Let's we do one more time for this one. So mc2, when I differentiate this, can we write ym minus 1 directly? Why? Because m minus 2 plus 1 is minus 1 v2. Then um minus 2 as it is, then v3. Any doubt? Special part is here. Listen carefully. Plus dot dot dot. mcr is a constant term. Listen carefully. Clear? So what is the derivatives of this? Okay, just tell me, dear. Can you tell me what is the just previous values of here? If I write down the series, what will be the previous value? It is mcr minus 1. Yes or no? mc, if it is 1, it is 2 mcr minus. Then u power is what? M minus r plus 1, then vr minus 1. Any doubt this one? This minus this, because this minus this, minus r minus minus will become plus, and vr minus 1. Clear? So look over. So because we are proving with the help of mathematical induction, so we have to create a same series. That if it is m plus 1, you have to prove each and everywhere is m plus 1 only. So if I common mcr minus 1 over here, so here I am applying u into v. Okay, so what is a u into v? Again check it. So u, when I differentiate this, it become m minus r plus 2, then vr minus 1 as it is, plus u m minus r plus 1. When I differentiate this, it become vr only, plus mcr is a constant term. When I differentiate this, it become u m minus r plus 1 vr as it is, and then again keep m minus r as it is, differentiate this r plus 1. In this way you have to do. At last I am differentiating this. U I differentiate, it become u1, then it become bm as it is, plus u as it is. When I differentiate, it is bm plus 1. If you understand up to here, then your theorem is solved. This is the main part. Differentiate. Now all we have to do arrangement only. Arrangement using the properties of the combination. Clear? So listen carefully. Clear? Now look over. So keep this as it is, because you know very well, if it is m plus 1 here, you need here m plus 1, here m plus 1 in this way. You need here also m plus 1 minus 1. That means you just need m only. So listen carefully. Okay, you'll write this over here. Well, first listen carefully, then copy. Okay, because this part is very important. This final line is very important. Arrangement plus. Dear, if you see this one, isn't it? It is also um beyond. So if we take this from here, if we common umv1, so it become what? 1 plus, can we write mc1 as a m only? Clear? Or don't worry, I'll write this only, mc1. So mc1, so in bracket you can write umb1. Any doubt, Megal? I'm just taking from here, and if you open the bracket, what is common? U to the power u suffix m v1, if you common, it become 1 and plus mc1. Am I clear? From this part and this part. Clear? When I open the bracket, it becomes what? Um minus 1 v2. Here also you'll see when I open bracket um minus 1 v2. So when you common out, common um minus 1 v2, so you are getting what? Tell me what you are getting. In one bracket you are getting mc1 plus mc2 um minus 1 v2. Yes or no? When I multiply this with this and this with this, check it, isn't it? You are getting um minus 1 v2, same. So what is the common? mc1 plus mc2. Any doubt? From here, if we see this part, dear, if we see this part and this part, isn't it? It is same. Check it. Exactly same. Forget about this. So if we think that's all, where does this part and this part will go? So it is a dotted figure series. There is many terms over here. So I'm hiding on the dotted figure. I'm only dealing with the m plus 1 part. Clear? So when I multiply this with this dear and this with this, so in bracket you are getting what? mcr minus 1 plus mcr u m minus r plus 1 and vr. Any doubt? I'm just multiplying. If you think that's how, where does this go? This goes in the dotted figure and this goes in the, at last. Can we write, I can neglect this one and write this as a what? Last part is u v m plus 1. Copy this up to here. Any doubt? Clear? Clear this one? Main part is whenever you have to make a common part. So listen carefully. Because why induction is very easy? Because you know what you need to answer. You know what you need to answer. So listen carefully, okay? Not selecting. Just wait. So look on. Now all we have to use the formula. So give this equation as a 2, okay? 1 2 you can 1. I've not given any equation. No. Give this equation was 1. Select it. किसी नहीं. चलो look over, okay? So now listen carefully. So we have a property, many property. So I hope you know what you have to prove. Listen carefully. Because if you notice this one, dear, because all you have to need here, dear, if it is m plus 1, here should be m plus 1, yes or no? Here should be m plus 1, here should be m plus 1, here should be m plus 1, here last should be m plus 1. We have already proven this way. All we have to arrange this bracket part only using properties of combination. Clear? So listen carefully. So now I am using the property. So dear, can we write 1 plus mc1? I'm just simplifying this. So 1 plus mc1 is 1 plus m, yes or no? Because mc1 is m. So can we write this as a dear m plus 1 c1? Because I have to write in combination format. It is same. As I have already told you that 6, if you want to write in combination, you can write 61. Both are same. Any doubt? Clear? This part. So mc1 plus mc2. If both are the same, so power will add and then bigger value you have to write. Which is bigger, 1 or 2? Power in n you have to add n plus 1 using that property. Am I clear? Similarly that one. So mcr minus 1 plus mcr. When the this n is same and this is just differ by only 1, so you just have to add 1, and which is bigger? R minus 1 or R is bigger, so you have to write this. Any doubt there? So all I'm just using here, here and here what properties only. So I'm writing using 2 on where 1 we get what you get uv m plus 1 as a here this is also m plus 1, I think. It yes, it is m plus 1. I just copy wrongly, okay? It is m plus 1 u m plus 1 v. Am I clear? This u m plus 1 and then I'm coming. Clear? So that means this is u m plus 1. So look over. So u m plus 1 V plus. In place of this, I can write what? M plus 1 C1 and U. Listen carefully. Yeah? Look. So you have to arrange in a proper order. What is the formula? U M plus 1 V, this minus this. So you have to write on this M as a M plus 1 minus. You have to write, mention in this way. Clear? Plus. What is the next one? This can be written as a what? M plus 1 C what? C2. So you have to write in U M plus 1 minus 2. You check, it is same only. You have to write in the general format. Am I clear? So V2 plus dot figure. You can write this as a M plus 1 CR U. You have to write a M plus 1 minus R. It is same. If you check, it is same. So VR. At last, U Vm plus 1. Isn't it? It is proved. Check it. See this theorem. What is our theorem? If it is n, it is n u n v plus n c1 u n v in this way. If it is m plus 1, it should be m plus 1, here m plus 1, here plus m plus 1 minus 1, so on. So check it. We have proved it is true for n equals to m plus 1 also. Check it. M plus 1 v m plus 1 c1 u m plus 1 minus 1 v1 plus m plus 1 c2 u m plus 1 minus 2 v2. Clear? Any doubt? Clear? So therefore, we can see that what? Pn is true for n is equals to m plus 1. Hence, by what? Principle of mathematical induction, Pn is true for all n belongings to natural number. So this is the proof of the Leibniz theorem. Clear? So that means you should know the principle of induction, how to prove any theorem using principle of induction, and you should know the arranging also. So here in arranging, main part in arranging from this to this is important. Here you have applied what? Combination property. Clear? In the next we'll do what? We'll do application of the Leibniz theorem as well. How to apply Leibniz theorem. Clear?